Mixing different voltages in an electrical system is generally not recommended. This is due to the potential for confusion, possible equipment damage, and increased safety hazards. While there aren't specific code sections that directly prohibit mixing voltages in a single system, it's extremely important to make absolutely sure that all of the equipment being used is properly rated for the voltage that's being provided to it. A panel board marked as 208 volts specifically requires careful evaluation by a qualified electrician. This evaluation will determine whether or not it's actually compatible with a 240 volt generator. If the panel board is not explicitly rated to handle 240 volts, then it has to be replaced to ensure safety and prevent any equipment failures. The Chicago Code has particular requirements for sizing emergency lighting generators. These generators need to be sized so that they handle no more than 80% of the total connected load. Accurately determining the connected load is very important. It should be based on the specific space that's being served and the exact lighting requirements for that space. Given the information available, it is recommended that voltage levels are not mixed within the electrical system. The existing panel board should be replaced with a new one that is rated for both 208 volts and 240 volts. The generator should be sized based on the actual connected load, and it must adhere to the 80% load limit as mandated by code. If there are concerns about voltage compatibility, it might be worth considering installing a new 208/120 volt three-phase service. The automatic transfer switch, or ATS, plays a critical role and has to be fully compatible with both the generator and the utility service to ensure a seamless transfer of power. All of the wiring and the connections need to be thoroughly inspected and rigorously tested by a qualified and licensed electrician. This inspection and testing is necessary to guarantee proper operation and to ensure safety across the entire system. Regular maintenance and frequent testing should be standard practice for both the generator and the ATS. These practices are critical to ensure reliability and to prevent any potential hazards from occurring. The primary reasons for avoiding mixing voltage levels in an electrical system are firstly, safety. Equipment designed for one voltage level may not operate safely or reliably at a different voltage. This can lead to overheating, electrical shock, or even fire hazards. Secondly, equipment damage. Applying the wrong voltage to electrical equipment can cause immediate damage or reduce its lifespan. This is especially true for sensitive electronic devices. Thirdly, code compliance. While there isn't a blanket prohibition against mixing voltages, electrical codes often require that all equipment be rated for the voltage supplied. Mixing voltages can make it difficult to meet these requirements. Fourthly, confusion. Mixing voltages can create confusion for maintenance personnel and others who work on the electrical system. This can increase the risk of errors and accidents. To determine compatibility with a 240 volt generator, a qualified electrician should inspect the panel board. The electrician will look for a voltage rating label on the panel board. This label will indicate the maximum voltage that the panel board is designed to handle. If the label indicates that the panel board is rated for 240 volts or higher, it's generally considered compatible. However, a visual inspection is also important. The electrician should look for any signs of damage or wear, such as cracks, corrosion, or loose connections. If any damage is found, the panel board should be replaced, regardless of its voltage rating. To accurately determine the connected load, you'll need to consider all of the electrical devices that will be powered by the generator. This includes lights, appliances, and any other equipment that will be used during a power outage. For each device, you'll need to determine its power consumption in watts. This information is usually found on the device's nameplate or in its user manual. Once you have the power consumption for each device, you can add them all up to get the total connected load. It's important to include a safety factor in your calculations. This will account for any unexpected loads or increases in power consumption. A safety factor of 25% is generally recommended. To calculate the generator size, you'll need to divide the total connected load by 0.8, which represents the 80% load limit required by the Chicago Code. This will give you the minimum generator size in watts. It's always a good idea to choose a generator that is slightly larger than the minimum required size. This will provide some extra capacity and ensure that the generator can handle any unexpected loads. Here's a step-by-step guide to sizing a generator for emergency lighting. Firstly, identify all emergency lighting fixtures and equipment. This includes all lighting fixtures, exit signs, and other equipment that must operate during a power outage. Secondly, determine the power consumption of each device. Check the nameplate on each fixture or piece of equipment to determine its power consumption in watts or volt amps, abbreviated as VA. Thirdly, calculate the total connected load. Add up the power consumption of all the emergency lighting fixtures and equipment to get the total connected load in watts or volt amps. Fourthly, apply the 80% load limit. Multiply the total connected load by 1.25 to account for the 80% load limit. This will give you the minimum generator size in watts or volt amps. Fifthly, select a generator. Choose a generator that is rated for at least the minimum generator size calculated in the previous step. It's always a good idea to choose a generator that is slightly larger than the minimum required size to provide some extra capacity. Sixthly, verify code compliance. Check with your local electrical code to ensure that the generator installation meets all applicable requirements. Automatic transfer switches, abbreviated ATS, are essential components in emergency power systems. They automatically switch the electrical load from the utility power source to the generator when a power outage occurs. Several factors must be considered when selecting an ATS, including firstly, voltage compatibility. The ATS must be compatible with both the utility power source and the generator. This means that it must be able to handle the voltage and frequency of both sources. Secondly, current rating. The ATS must be able to handle the maximum current that will be drawn by the load. This is determined by the total connected load of the emergency lighting and equipment. Thirdly, transfer time. The ATS must be able to transfer the load from the utility power source to the generator quickly and reliably. The transfer time is the amount of time it takes for the ATS to switch from one source to the other. A shorter transfer time is generally better, as it minimizes the interruption of power to the emergency lighting and equipment. Fourthly, features. ATS come with a variety of features, such as automatic testing, remote monitoring, and data logging. Choose an ATS that has the features that are most important for your application. Fifthly, reliability. The ATS is a critical component of the emergency power system, so it's important to choose a reliable ATS from a reputable manufacturer. Here are some additional considerations for ATS installations. Firstly, location. The ATS should be installed in a location that is easily accessible for maintenance and testing. It should also be protected from the elements such as rain and snow. Secondly, wiring. The wiring for the ATS should be properly sized and installed according to the manufacturer's instructions and all applicable electrical codes. Thirdly, grounding. The ATS must be properly grounded to protect against electrical shock hazards. Fourthly, testing. The ATS should be tested regularly to ensure that it is operating properly. This testing should include both automatic and manual transfer tests. Voltage compatibility issues can arise if the generator and the existing electrical system operate at different voltage levels. For example, if the generator supplies 240 volts and the existing system is designed for 208 volts, there could be problems. Equipment rated for 208 volts may be damaged if it is connected to a 240 volt source. To avoid voltage compatibility issues, it's important to ensure that the generator and the existing electrical system operate at the same voltage level. If this is not possible, a step-up or step-down transformer may be required to adjust the voltage to the appropriate level. A new 208/120 volt three-phase service can provide several benefits. Firstly, voltage compatibility. A 208/120 volt three-phase service is compatible with most standard electrical equipment. This eliminates the need for step-up or step-down transformers. Secondly, increased capacity. A three-phase service can provide more power than a single-phase service. This can be beneficial if you plan to add more electrical equipment in the future. Thirdly, improved efficiency. Three-phase power is more efficient than single-phase power. This can result in lower energy costs. However, there are also some drawbacks to consider. Firstly, cost. Installing a new three-phase service can be more expensive than using the existing single-phase service. Secondly, complexity. Three-phase systems are more complex than single-phase systems. This can make them more difficult to install and maintain. Thirdly, space requirements. Three-phase equipment typically requires more space than single-phase equipment. Electrical codes, such as the National Electrical Code, abbreviated NEC, provide guidelines for electrical installations to ensure safety and prevent hazards. While the NEC doesn't explicitly prohibit mixing voltages in all situations, it emphasizes the importance of using equipment that is rated for the applied voltage. The NEC also covers requirements for emergency power systems, including generators and automatic transfer switches. Some relevant NEC sections include NEC 110.3. It is for examination, identification, installation, and use of equipment. This section requires that all electrical equipment be installed and used in accordance with its listing and labeling. This means that the equipment must be rated for the voltage and current that it will be subjected to. NEC 445 is for generators. This article covers the installation and wiring of generators. It includes requirements for generator sizing, overcurrent protection, and grounding. NEC 700 covers emergency systems. This article covers the installation and wiring of emergency systems, including generators, automatic transfer switches, and emergency lighting. It includes requirements for system design, testing, and maintenance. NEC 701 addresses legally required standby systems. This covers systems that are legally required to operate in the event of a power outage, such as fire pumps and elevators. NEC 702 is for optional standby systems. This covers systems that are not legally required but are installed to provide power for convenience or business continuity. These systems have less stringent requirements than emergency or legally required standby systems. Regular maintenance and testing are crucial for ensuring the reliability and safety of emergency power systems. A qualified electrician should perform regular inspections and maintenance on the generator, automatic transfer switch, and other components of the system. Testing should be performed to verify that the system is operating properly and that it can provide power in the event of an outage. Maintenance procedures should include changing the oil and filters in the generator, inspecting the batteries, and cleaning the contacts on the automatic transfer switch. Testing should include both automatic and manual transfer tests to verify that the system can switch from the utility power source to the generator quickly and reliably. Detailed documentation of all maintenance and testing activities should be maintained. This documentation should include the date of the maintenance or testing, the name of the person who performed the work, and any findings or observations. All wiring and connections should be inspected and tested by a qualified electrician to ensure proper operation and safety. Look for loose connections, damaged wiring, and signs of corrosion. Use appropriate testing equipment, such as a multimeter or circuit tester, to verify that the wiring is properly connected and that there are no shorts or open circuits. Follow all safety precautions when working with electrical wiring and connections. Wear appropriate personal protective equipment, such as safety glasses and gloves, and de-energize the circuit before working on it. The potential hazards of mixing voltages in an electrical system include, firstly, electric shock. If equipment is not properly rated for the voltage being supplied, it can become energized and pose a risk of electric shock. Secondly, fire. Overloaded or improperly wired equipment can overheat and cause a fire. Thirdly, equipment damage. Applying the wrong voltage to electrical equipment can cause damage to the equipment and shorten its lifespan. Fourthly, system failure. Mixing voltages can cause the electrical system to malfunction or fail, leading to power outages and other problems. To minimize these risks, it's essential to follow all applicable electrical codes and standards, use equipment that is properly rated for the voltage being supplied, and have all electrical work performed by a qualified electrician. When evaluating an existing panel board for compatibility with the 240-volt generator, a qualified electrician should perform a thorough inspection of the panel board and its components. This inspection should include, firstly, visual inspection. The electrician should visually inspect the panel board for any signs of damage, such as cracks, corrosion, or loose connections. Secondly, voltage rating. The electrician should check the voltage rating of the panel board to ensure that it is rated for 240 volts or higher. The voltage rating is usually found on a label on the panel board. Thirdly, component ratings. The electrician should check the voltage and current ratings of all components in the panel board, such as circuit breakers and fuses, to ensure that they are rated for 240 volts. Fourthly, wiring insulation. The electrician should check the insulation on the wiring in the panel board to ensure that it is in good condition and that it is rated for 240 volts. Fifthly, grounding. The electrician should check the grounding of the panel board to ensure that it is properly grounded. If the panel board is not rated for 240 volts or if any damage is found, the panel board should be replaced. The electrician should also ensure that all wiring and connections are properly sized and installed according to applicable electrical codes. Consider upgrading to a 208/120 volt 3-phase service. This can provide several benefits, including voltage compatibility, increased capacity, and improved efficiency. However, it's important to weigh the costs and benefits of upgrading to a 3-phase service before making a decision. Also, consult with a qualified electrician to determine if a 3-phase service is right for your needs. If a new 208/120 volt 3-phase service is installed, the existing single-phase panel board should be replaced with a 3-phase panel board. The 3-phase panel board should be sized to accommodate the existing load and any future load growth. The electrician should also ensure that all wiring and connections are properly sized and installed according to applicable electrical codes.